Hi everyone! In this video we're going to be learning about curves in space and their tangents. So let's begin by considering an object that's moving through space during a specific amount of time, so we're going to call that a time interval. And now this is going to lead into a vector function. And so the object's path, this object that's moving through space, the object's path is actually a curve. So is the curve made of points x, y, z, because we're in 3D space, of points x, comma, y, comma, z. And this is where we're going to define functions for x, y, and z. So where f of, we'll say t, our input is going to be t, we can think of that as time, represents the x component. And then we'll say g of t is y, and then we'll go h of t is z. Okay, and this is for t values in some interval I. Okay, so this symbol just means belongs to. So t belongs to this interval I. Okay, so we have an object whose path is defined by this curve, and that curve is made up of a bunch of points in 3D space, and each component of this point, x, y, and z, is made up of a function of t, where you plug in t and get out these x, y, z values. So now, and you can say that here actually, we'll say functions of time. Functions of time if we're talking about our input being time. So that's the f, g, and h. So a vector form of a curve is what we're going to define now. So vector form of a curve is the following. So we're going to say r of t, that's our function, that's a vector function, where t is the input. It's actually just a vector, we're going to say from O to P. So vector OP, which breaks down as f of t I, so in the x direction, or the I component of your vector, plus g of t j, plus h of t k. Alright, so this is how you can represent a curve using vectors. So we move whatever f of t is in the I direction or in the x direction, similar for j and k, and then that's how we locate all of our points in space, and all those points put together form this curve. And the curve could represent some object that's traveling through space. Now this is a vector function. So this is a vector function which differs from our functions from the past. So until now, everything was basically a real number valued function, which we're going to start calling scalar functions. And I'll write that down. But basically, let's move up here and then describe this a little bit better. So this is a vector function, which is basically a rule. So a rule that assigns a vector. So a rule that assigns a vector to each domain element. So every t number, t value element, excuse me, that you plug in, every number you choose for t, and if this is time, maybe 1 second, 2 seconds, 3 seconds, every t that number that you plug in, you're going to get a vector out as your output. And so let me just draw you a quick sketch. Hopefully it makes sense if you can visualize it. So let's get rid of this part. So I am trying to draw 3D space here. My z, x, and y axes. Okay, so let's just label those really fast. And so what all this is saying is that I have some object that's traveling through space. Maybe it does something like this. So the object's doing something like that. Okay. Now every single point on this curve can be represented by an xyz point, but also a vector from the origin to that point. And so if I kind of just pick a spot here, let's go right here. We'll call this point P, and there's a vector from the origin to this point, and that's this vector OP or r of t. And you can do this infinitely many times all along this curve for whatever t, the range for t is. This t starts here, whatever this is here, and t stops here. Okay, your time interval or your t interval. So your object can travel along like this, and we can represent each of the points in space using a vector. So let me give you a few more notes about this type of vector function, and then we'll look at an example. So note, we'll write it over here, note that f, g, and h are called component functions, and that's because they give us the components of our vector, the x, y, z components. Then also, next note, and I mentioned this a moment ago, the functions that give you a real number, we're going to kind of rename those a little bit so that it's more clear. So real valued functions are now, we could just say are now called scalar functions. And this is just to distinguish them between vector functions. So we'll say are called scalar functions. And again, the only reason for this is just to be distinct. If I know I'm working with vectors, I can call it a vector function. If I know I'm working with numbers, that's a scalar function. Then, just putting these two things together, the components, if you think about it, if you plug in numbers for t into our functions f, g, and h, the components are actually all scalar functions, because you're going to get a number out that tells you where to plot your point in terms of x, y, and z. Scalar functions. Okay, so let's take a look at one of these vector functions, and I'm going to graph it on the computer with you guys just so it's a better drawing, but let's work it out here first. So we are going to graph r of t equal to cosine of t I plus sine of t j plus t k. Alright, and if you want, you can put your vector notation on I, j, and k. Or you can also use the component form. If you prefer that, let me just remind you, this is always an option. So if you'd rather use this notation, just make sure to use your angled brackets. You could say cosine t, comma, sine t, comma, t. These are equivalent. Alright, now, I only want this for certain t values. So I want to consider this function for t between 0 and 2 pi. So I'm going to actually make a table, not an xy table, and actually an xyz table, and t to get some points to plot. So I'm going to make a table where t is my input, but my output is actually x, y, z. So if you think about it, x, y, and z, you have to take the components here. So x is cosine t, and then y is sine of t, and then z is t. And so the points in space are x, comma, y, comma, z. Alright, so we're told to go from 0 to 2 pi. I'm just going to pick a handful of values to plug in. I'm going to plug in 0, pi over 2, pi, 3 pi over 2, and 2 pi. And you can definitely plug in more, especially if you're not able to see what you're plotting, like the shape of the path. But we're going to go here and then I'll show you what this looks like. So basically you're just going to plug these each into x, y, and z, your three functions. This was x equaled f of t, so this is like the function f of t. This was your function g of t, and this was h of t. So let's just do the first row together and then I'll fill that in for you real quick. So cosine of 0 is 1, sine of 0 is 0, and then z is the same as t, so whatever t is here is just our z value. So our first point that we would actually plot is 1, 0, 0. Alright, so I'm going to fill this in. Feel free to pause it and fill it in yourself before I do. Okay, are you ready? I'll show you what I got. So I did use the decimal versions of your numbers. You might have had like pi over 2, pi, and so on here. But the reason I'm picking decimals is because I'm going to have to plot the points, and I kind of need to know where to plot them, and decimals for me is the best way. So let's just plot a few of these, and then I'll show you on the computer how this actually looks, so it'll hopefully look a little better than my hand drawing. So 1, 0, 0, 1 in the x, 0 in y and z, so that point's right there. Then 0, 1, 1.57, so nowhere in the x, but or other than 0. Then I'm going to go 1 in the y, and then from here I'm actually going to go up to 1.57. So if I kind of make a mark, that's right here on my z-axis, but remember this is kind of tilted. This whole axis is sort of tilted so we can see it. So that point's about right there. Let's do another one. So -1 in the x, so I'm actually going to go backwards here. -1 in the x might be right there. 0 in the y, so I'm still right here. And then I'm going to go up to 3.14. So 3.14 is about right here. And so if I kind of angle that based on my drawing, that's about right here. And then you can keep doing this. And so what's happening, because this is a three-dimensional path of whatever object is traveling on this path, it's actually kind of going up and around like that. So let me show you what that looks like with a computer software so you can see it a little better. Here's this graph that we just drew, and notice it's between t values of 0 and 2 pi. So here was our first point at 1, 0, 0. And then if we kept plotting all the points, and if we picked more values for t, we would have gotten this blue path here, and that this particle follows and goes up and up and up. Okay, so what I want to talk to you about next is limits and continuity of vector valued functions, and then after that it's going to be derivatives. So what we're going to talk about for the rest of this video is these two things, limits and derivatives. So it's going to sound very familiar, hopefully, because it'll look like things you learned from Calculus 1. And we're just basically kind of redefining them here for vector functions. So remember the distinction. There's vector functions that your input produces a vector. And then there's scalar functions where your input produces a number. So everything you kind of know about scalar functions getting defined for vector valued functions. So starting with letting your vector function, which we defined before, our I, j, and k, or x, y, and z components, we're going to let it be defined on some domain, we're calling D, and let L be a vector. So I'm going to give you your limit definition here. And so it's going to look like this. If for every epsilon greater than 0, so this is Greek epsilon, there exists delta greater than 0, so Greek delta, such that for all t belonging to our domain, so t in our within our domain, then the following is true. So I'll explain it when we write it. So we have the absolute value of the difference from r of t to L. Okay, and these are both vectors. Okay. This is going to be less than epsilon. And this is going to be true whenever the distance or absolute value from t to t naught is less than delta. And then those combined, all of this means that the limit as t approaches t naught of our vector function, r of t, equals L. Okay, I know that's a little much, but let me explain. If you remember your precise limit definition from Calculus 1, this is actually basically it, just maybe you had an f of x here, okay? And then this probably wasn't t's, it was x's. But other than that, it's the same precise limit definition. But here's all it's saying. If you never saw this before, or if you're seeing it but you didn't really ever understand it, if I kind of just focus on two dimensions right now, if I say my output is r and my input was t, because remember r is a function of t. If I'm claiming that my function approaches this limit value, so remember how limits work, our output is getting really close to this limit value, and if we get really close to this input value. And so that might look like maybe my my t naught that I'm approaching is somewhere here. So I'm saying I'm getting really close to this t naught value. This can be any number in our domain. And my output value is maybe here. So this is like r of t naught. Okay, so that would be a point in space. All right. And all this definition is basically saying is if you sort of narrow down your viewpoint, if you kind of look really close to t naught, if you only sort of work your way close here and numbers around that, so you sort of create this small window that you're looking at, that window we're saying is less than some number delta. So right here to the left and to the right of this number, we're just saying that that's some number delta. So this little piece right there and this little piece right here are both the length delta, whatever that is. It could be like 0.1 or something like that. So it's just a really small gap to the left and right that we're kind of looking at. So when that's true, when we narrow down our focus for our input, then our output also gets narrowed down as far as what's going to come out of this function. So that might be like we're really close to r of t right here. And so our function value is actually right there. And so this same idea, I can't fit it, I didn't give myself very much room, but right in here, this is epsilon. So this little distance here is epsilon, same thing here. And so that was our, whoops, r right here, let me put that back, r of t naught. Okay, so if you've never seen this precise limit definition, or if you have, this is all it's saying. You kind of make sure you're really close, this distance on your x or input values is really close to what you're looking at. You're approaching some number here, t naught. And when you do that, then your y values, or in this case r values, your outputs get really close to having plugged in that number, and then you have the limit. So your function is approaching this limit, so L is actually, you know what, I should change this to L. This is L. It doesn't necessarily need to be r of t naught, unless it's a continuous function, which we'll talk about in just a minute. But this is what you're approaching. As your inputs get really close to t naught, your outputs get really close to L. Precise limit definition. Okay, so that's that one. I know it's a little weird, but let's look at an example really quick. So we'll compute one of these limits, and then we'll talk more about the continuity. Okay, let's get rid of that real quick. And so we are going to find the limit as t approaches, let's go pi over 4, and let's just use our example that we graphed. So we're going to find the limit of r of t, and from the previous example that was cosine t I plus sine t j plus t k. Alright, now here's the fun part. You don't have to do anything new that you haven't done in the past with limits. Try direct substitution. If it doesn't work, then you try another technique. If you kind of recall how limits worked, you had various techniques for how to simplify the functions. So in this case, let's just see, does direct substitution work? So if I just plug in pi over 4, so cosine of pi over 4, and that's going to be my I component, and then sine of pi over 4, and that's the j component, and then pi over 4 times, and that's the k component. Pi over 4. That got a little weird. That says pi. Okay, and remember, the component functions are all scalar functions. So this part's a number, this part's a number, and this part's a number, but together they form the vector function. And these are all going to work. So no problems here. Direct substitution worked. So cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is also square root 2 over 2. And then this is just what it was, pi over 4. Okay, and that's it. So this limit, our function, our vector function, approaches this vector when we plug in t values very, very close to pi over 4. And that's our final answer. So let me give you some last notes about continuity, and then we'll move on to the derivative parts of this. So I kind of mentioned it back here, we're approaching some limit, but to guarantee that a function is continuous, we have some facts about that. So let me give you a definition right here. If the limit as t approaches t naught of r of t equals r of t naught, okay, then, and I'll explain this, then r of t is continuous at t naught. Continuous at t naught. Okay, so I'm just going to get that over there. Basically, if you plug in the value you're approaching for your inputs, and it's the same as your limit, so your limit is approaching, your function is approaching one thing from taking the limit. Your function equals something from plugging in the number here that you were approaching. When those two things match, when they're the same, then it's a continuous function at that point. So this idea back here now is where I can officially put in the r of t naught. When this equals the same number I would have got by just plugging in t naught, then it's a continuous function. Because just so you're aware of like what's not continuous, if you kind of remember from the past, some discontinuities might be maybe something where, let me just kind of do it from this drawing. A discontinuity could occur like maybe where you had a point here, but the rest of your function sort of still approach that spot, that value. So that would not be true in that case. So it's continuous if that is true. Okay, so then let me give you a note also. So that's continuous at a point, at t naught. And then if we kind of generalize that, then it's continuous everywhere. So note, if r of t is continuous at every t in the domain that belongs to D, the domain, then r of t is a continuous vector function. Vector function. Okay. All right, so very straightforward if you think about it. If your function is continuous at every single point that you possibly plug in, then it's a continuous function. So the only distinction here is this is continuous at a point, this is continuous everywhere. All right, so now let's move on and talk about derivatives, which comes from after you learn limits. If you recall in Calc 1, you learn limits and derivatives, so we're doing the same thing here. So now we're going to talk about derivatives and motion. So we have our vector function here that we've been looking at, and the derivative of it. Okay, so the derivative is r of t prime. Okay, so we're going to just denote it like that. And I'm just going to leave off the vector notation because it's going to start looking kind of convoluted with some stuff, but feel free to put it on there if you want. So r of t prime, and you can write it with the prime notation, or you can say the derivative of r with respect to t. And officially, if you recall the limit definition for a derivative, here's what this looks like. So it's a limit as the change in t approaches 0. So let me explain this real quick. Delta t, this is capital delta. Delta t always represents change, some kind of change. So change in t is getting really small. Okay, that's what that's saying. And this expression here is going to be r of t plus delta t minus r of t all over delta t. Now, if you remember learning the limit definition for derivative in the past for Calculus 1 for scalar functions, this is the same thing. Let me just show you so you remember. If this might look more familiar, you don't have to write this. It was the limit as h approaches 0 of f of x plus h minus f of x all over h. So same idea. The t values, the change in them is getting really small. You're basically zooming in on one particular t value, and you're just saying this output value where I'm like a little bit further away from my original t minus the original output value, so that difference over the change in my my t values. it's essentially the slope formula still, if you recall. The difference in the outputs over the difference in the inputs. Okay, so now, if you don't recall that, or if you do, but you're like, I don't remember using that a lot, it's because you had differentiation rules. So you can basically break this down into the three components here, and you can just say that this derivative of this vector function is the derivative of f with respect to t, and that's in the I direction, plus the derivative of g with respect to t in the j direction, plus the derivative of h with respect to t in the k direction. And so you basically just take the derivatives of these three components, f, g, and h, and you can use your rules from derivatives from the past, so like your power rule and chain rule and things like that. And so we'll go through that. So let me give you another definition real quick. R of t is differentiable. So this vector function is differentiable at t if your component functions f, g, and h have derivatives at t. So as long as each of your component functions have derivatives at every t number you're plugging in, then your function is considered differentiable at that t number. And then just like we said with continuity, if a function was continuous everywhere, then it was called a continuous function. If a function is differentiable everywhere, it's a differentiable function. So let's just kind of expand on this definition here. So if R of t is differentiable, I'm going to abbreviate, differentiable at every point in D, so we'll just say in the domain, then, let's squeeze this in here, then R of t is a differentiable vector function. Differentiable vector function. Alright, I'm hoping that this stuff is sounding familiar if you remember what you learned in single variable calculus, Calculus 1. Same exact concepts, it's just now the function is a vector function. The output is a vector. Now, let me give you some facts, because what we are actually interested in here is how this might represent a particle moving in space, this function. And so what does the derivative tell us in maybe a more application kind of way? So let me give you some notes about that. Alright, so, fact, the derivative r prime of t is the vector tangent, okay, tangent to the curve, and this is going to be at the point, so at the point f of t, comma, g of t, comma, h of t. Okay, so just like before in single variable calculus, the derivative represented the tangent line. In this case, it's the tangent vector. Okay, so the vector tangent to your curve. Then we can say that the tangent line, so tangent line to the smooth curve, so this is just sort of a requirement, your curve does have to be smooth. So smooth curve at a point, which we'll call P, is the line through P, so through this point, let me erase this, through P, and then it's parallel, so parallel to the derivative r prime of t. Okay, at that point. So this statement here, if you want to find the tangent line, you find the derivative, which is a tangent vector, and then the tangent line is just parallel to that tangent vector, but it passes through your curve at the point you're focused on. And then one more thing here. Let's erase this. The derivative, r prime of t, this is a nice one here, this fact, always points in the direction of motion. Direction of motion. Okay, so now because you are working with vector functions and not scalar functions, your derivative has a direction. It's a vector, so it's pointing somewhere. So this derivative vector, it's pointing in the way your particle is traveling, or article. Object. So if you have some object moving through space and you take the derivative at a point, then at that point this vector, that's the derivative vector, will point the way the object is traveling. So that's a nice fact to use. So I just want to show you these differentiation rules for vector functions. So some of them are pretty straightforward from your rules for differentiation with scalar valued functions. U and V just represent differentiable vectors, vector functions, and C represents a constant vector. So you have your constant function rule right here, number 1. The derivative of a constant vector is 0. Scalar multiple rules, you can factor out that scalar and then take the derivative that way. Just like you did with scalar valued functions and derivatives. Then right here, this is basically like your product rule if you expand this out. So f of t represents a number, scalar function would come out of here, and then u of t would be a vector or vector function, so vectors would come out of here. So you would just take derivative of the scalar function right here, f prime, times your vector function, plus the scalar function times the derivative of the vector function. So that looks similar to the product rule from single variable calculus and scalar valued functions. So sum and difference rules, very straightforward there. You have a dot product rule now, and then notice that breaks down very similar to the product rule. So when you take the dot product of two vectors, it's the derivative of the first vector function dotted with the second vector function, plus the first vector function dotted with the derivative of the second vector function. And then we have a cross product rule, very, very similar in what you do here. When you take the derivative of the cross product of two vectors, it looks very similar to the product rule. And then the chain rule, if you have the vector function of a scalar function, then you have your derivative of the inside and then times the derivative of the outside, which is your vector function. Alright, so we're going to stop this one here, and in the very next video we're going to talk more about the motion of like a particle or object moving in space and look at some examples. Alright, so see you soon.